Let's dive right into this explainer. You know, when you walk past a massive skyscraper or a busy highway construction site, you've probably wondered how engineers actually know the ground can support all that weight. We tend to think of dirt as, well, just dirt. But the truth is, a simple pile of soil has to go through a fascinating, highly rigorous audition process before we'd ever dare to build anything on top of it. It really makes you wonder, right? Is all dirt created equal, or does it literally have a resume? Today, we're going to follow the epic journey of a single soil sample, from being scooped out of a messy field to being poked and prodded in the lab. We're going to see exactly how geotechnical engineers translate physical dirt into a precise mathematical grade. So here is our roadmap for today. We'll start with the dirt on soil, move into shaking it up with sieve analysis, settling down with hydrometer analysis, plotting the curves, the unified soil classification system, and finally, grading for highways. All right, part one, the dirt on soil, defining the extremes. Let's look at the big picture. Classifying soil is really just about figuring out the size range of the particles in your sample. You're basically sorting the big chunky rocks from the microscopic specks. And in geotechnical engineering, there is one ultimate dividing line. It's the 0.075 millimeter mark. In the US standard, that's the number 200 sieve. That microscopic threshold is the grand divider. It splits coarse gravel and sand on one side from microscopic silt and clay on the other. Literally, everything else we do depends on which side of that tiny line our dirt lands on. Moving right along to part two, shaking it up, sieve analysis. So for the larger, coarse-grained stuff, your sands and your gravels, our first stop in the lab is a purely physical test called sieve analysis. Imagine a machine that acts exactly like a coin counter, sorting your loose change. First, you take the soil and completely oven dry it. Then a specific weight of that dirt is dumped into the top of a mechanical stack and just violently shaken. Inside that stack is a series of metal screens with progressively smaller openings filtering the material all the way from top to bottom. As it falls, the soil gets trapped at different levels. The number 4 sieve catches the gravel, the number 10 grabs the coarse sand, and it keeps going all the way down to that incredibly fine number 200 sieve we just talked about, with its tiny 0.075 millimeter opening. By stopping the shaker and weighing the dirt that got stuck on each screen, engineers can figure out exactly what percentage of sand and gravel is in the sample. Which brings us to part 3, settling down, hydrometer analysis. But hey, what about the dust? The stuff that's so incredibly fine it falls straight through that bottom number 200 screen. You can't just shake fine-grained silts and clays through a screen. It just won't work. So we switch gears to hydrometer analysis. This is actually based on the principle of sedimentation. We basically take that fine dirt, drop it into a tall glass jar of water, and watch how fast it sinks. Since different particles settle at different speeds based on their size and weight, engineers can map out those microscopic grains just by timing how long it takes them to hit the bottom. And honestly, the irony here is just amazing. To figure out the size of microscopic mud particles, engineers have to bust out high-level fluid dynamics. They rely on Stokes' law. They have to assume the dirt particles are tiny little spheres, and then run complex equations that factor in the water's temperature, viscosity, and specific gravity. All of that math, literally just to quantify dirt sinking in a jar of water. It's this beautiful intersection of high-level physics and, well, literal mud. Okay, part 4, plotting the curves, turning dirt into data. So once we're done shaking our coarse dirt and settling our fine dirt, we are left with a mountain of raw lab data. The next move is taking all those physical weights and times and turning them into a visual story. We plot them on a logarithmic scale to reveal the soil's true character. If the plotted line drops straight down, the soil is poorly graded, meaning almost all the particles are exactly the same size. But if it stretches out into a nice smooth S shape, it's well graded. That means it has a strong, diverse structural mix of large, medium, and small particles that fit tightly together like a giant puzzle. Now, visuals are great, but at the end of the day, engineers need hard math. So we use 2 key parameters, the uniformity coefficient, or CU, and the coefficient of gradation, or CC. We pull specific data points from our curve, specifically the diameters where 10, 30, and 60% of the soil passes through. By calculating these coefficients, we perfectly convert those swooping visual curves right back into cold, hard, usable numbers for our structural formulas. All right, part 5, the unified soil classification system. Naming the dirt. The whole point of all this intense testing is to finally give the soil its official grade. For general engineering, we use the Unified Soil Classification System, or USCS. A fun fact here, Arthur Casagrande originally developed this system during World War II specifically for the Army Corps of Engineers, so they could quickly classify soil to build bomber airstrips. It combines specific letters into a universal shorthand. So if you mix G for gravel and W for well-graded, bam, you've got a GW soil. Or if you have silt with high plasticity, that's an MH. It's super simple, elegant, and engineers everywhere speak this exact same language. And all of those symbols build up into a master matrix. When you look at flowcharts used by agencies like the California Department of Transportation, you can see the logic playing out. Every single sieve weight, every hydrometer calculation, and every coefficient we just talked about leads you down a very specific path. It's foolproof. It guarantees that whether you've got a poorly graded sand or a fat clay, it ultimately lands in one specific, scientifically definitive box. Finally, Part 6, Grading for Highways, the AASHTO standard. Now, while the USCS is fantastic for airstrips and building foundations, the roads we drive on every day actually use a slightly different standard. It's known as the AASHTO system, which stands for the American Association of State Highway and Transportation Officials. And there's a big difference here. The unified system calls a soil fine-grained if more than 50% passes that number 200 sieve. But AASHTO shifts the math, drawing the line at just 35%. Why the change? Because AASHTO has one laser-focused job, figuring out if a soil is physically tough enough to act as a stable subgrade for the constant heavy pounding of highway traffic. By mixing the sieve data with the soil's plasticity, which is basically how it behaves when it gets wet, AASHTO literally grades the dirt on a scale. An A1 rating, that means you've got an excellent rocky, granular soil that is absolutely ready to pave over. But as you slide down into the silt and clay materials, you hit those A4 to A7 ratings. Those are considered fair to poor for subgrades. Trust me, if a highway engineer sees an A7 soil, they know they have to dig it all out and replace it. Otherwise, that highway is guaranteed to crack and collapse under the pressure of passing 18-wheelers. It is honestly incredible to think about, right? The literal, everyday ground we walk and drive on has been rigorously sorted, plotted, and mathematically graded. It's not just dirt anymore. It's engineered data. So the next time you're cruising down a beautifully smooth stretch of highway, ask yourself, are you enjoying the asphalt? Or are you actually enjoying the perfectly well-graded, A1 certified soil doing all the heavy lifting underneath? Thanks so much for joining me on this explainer, and keep looking deeper into the ground beneath your feet.